So an example would be, let's go back to maybe a similar example to what we saw before. Let's say that r of t is equal to the sine of t 3 times the cosine of t, and then 4 plus t. If I want to know what the derivative of this vector valued function is, I just take the derivative of each of the components. So the derivative of sine is cosine of t. The derivative of cosine is negative sine. The 3 is just a coefficient, so I end up with negative 3 sine of t. And the derivative of 4 plus t, derivative of 4 is 0 because it's a constant, and the derivative of t is 1. So this is my derivative function. Let's look at the geometry. What is actually going on here? Let's look at a picture of what our r of t plus h minus r of t looks like. Let's say that we have a vector valued function and it traces out some path in 3-dimensional space. This line, this arcing line, is meant to indicate the tips of all of the vectors as the vector changes as time shifts. And we're going to call this r of t. And let's look at it at one particular t naught. So if I'm considering what is r of t naught plus h minus r of t naught. Well, let's say that this vector is the one that represents r of t naught. So this is the vector when t is equal to t naught. And so this vector right here is given by the vector r of t naught. And now I'm going to add h to it, to t naught. So that means that I'm moving forward a little bit in time. And I get a new vector, and I'm going to call this vector r of t naught plus h. So time has increased by a little bit. That little bit is h amount. And if I look at the difference of these two vectors, vector subtraction gives me this new vector. So this new vector is the vector that is the difference, r of t naught plus h minus r of t naught. This new vector, this difference vector, notice as h gets smaller and smaller, well, I take this difference vector and then I divide it by h. The limit as h goes to 0, our h's are getting smaller and smaller and smaller. It doesn't actually shrink the vector. What you end up getting is a tangent vector. So I'll write that to keep that on the board, that r prime at t naught is the tangent vector for when our time is equal to t naught. Why is this important? The tangent vector, so as I trace out this curve, as I get a tangent vector, that tangent vector is actually representing the velocity. It's representing the velocity because velocity in this case has a direction and it also has a magnitude, which is indicating the speed. We'll talk about that more in a following section. But the tangent vector we could also call the velocity vector. So if I want to know if this is tracing out the position of a particle through time, and I want to know what is the tangent vector at any given time, I take the derivative of my function. One more definition, and then we're going to look at an application. So the next definition is integration. And thankfully, there's nothing really all that new to know here. When I want to integrate, integration of vector valued functions, so when I want to look at integration of vector valued functions, this is going to be very similar to what we saw with differentiation. And if I'm looking at the integral from a to b of r of t dt, that's going to be exactly equal to the integral of each of the component functions. The integral from a to b of x of t dt, comma, integral from a to b of y of t dt, and the integral from a to b of z of t dt. Why is this interesting? This is where we get to the application part. Let's say that r of t is indicating your position. We just talked about how taking the derivative of our position vector will give us our velocity vector. And if we take the derivative of the velocity vector, or the second derivative of our position vector, we end up with our acceleration vector. So, for example, let's say that we have some spaceship traveling through space. And that spaceship has a position vector given by r of t is equal to 3t t plus 4 e to the t. So I'm going to revise this and make it t squared plus 4. That'll make it a little more interesting. And if I want to know what is its velocity when t equals 5, we can see, let's see, it's velocity and acceleration when t equals 5. Well, our velocity, r prime of t, is the derivative, which is given by 3, 2t, as I take the derivative of the second component function, and the derivative of the third component function is just itself, e to the t. So that means that our velocity is given when our derivative, when t is equal to 5, would be 3, 10, e to the 5th. This is our velocity vector. What's our acceleration vector? Well, that's going to be the second derivative. And the second derivative in this case, the derivative of 3 is 0, the derivative of 2t is 2, and the derivative of e to the t is still e to the t. And so if I plug in when t is equal to 5, I get 0 to e to the 5th. The reason why this is interesting is we can also work backwards. Let's say that instead of being given a position vector, we're given a velocity vector. If my velocity vector, v of t, was given as maybe sine of t, cosine of t, t, notice that this is also a helix. The helix is spinning in the opposite direction because the x's and the y's are flipped, but it's still spinning in the xy plane and as the z's increase when the t's increase. But this is my velocity vector. This isn't my position in space. This is the way that my velocity vector is moving as I move. How can I find out my position vector given this information? It turns out this isn't quite enough. If all I'm given is my velocity, I don't know where in the world I started. So I can't tell you where exactly I am if I don't know where I began. Let's say that at t equals 0, we had a position. I started at the point 1, 0, 0. Now we have enough information to be able to find out what our position vector is going to be. So to move backwards, if I know what the derivative is, I know that v of t is equal to r prime of t, which is given by this function, the function sine of t, cosine of t, t. If I know what the derivative is, I need to integrate with respect to t to be able to find out my position vector. This is a slight abuse of notation. But that means that my position vector, r of t, is going to be the integral of each of these components. So if the derivative of sine is cosine, the integral of sine is negative cosine. But wait! Anytime we integrate, you always need to remember that there could be a constant. And this is an important thing to remember, particularly with vector valued functions, because we're going to have a different constant for each of the component functions. The integral of cosine is sine. So the second component function is sine of t plus another constant. And the integral of t is 1/2 t squared plus a constant. So how do we figure out what these constants are? We need to use our initial position. So our initial position is this point, 1, 0, 0. And I'm going to say that means that r of 0 means that we're at the position vector 1, 0, 0, which is equal to this expression which we have above. And instead of writing out that expression, it means that when t is equal to 0, the negative cosine of 0 plus my constant has to be equal to 1. And I come up with 3 different equations setting each of these pieces equal to the initial position vector when my t is equal to 0. So I end up with negative cosine of 0 plus my first constant has to equal 1. Well, the cosine of 0 is 1, so the negative cosine of 0 is negative 1, and this tells me that negative 1 plus c1 equals 1, or my first constant is equal to 2. I do that again for the y component function. So I know that I start at y equals 0, so when y equals 0, the second component function, sine of t plus c2, where t is exactly equal to 0. Well, the sine of 0 is 0, so I know that 0 is equal to 0 plus the second constant, so the second constant is equal to 0. And then I have my third set of equations where I set my z equal to the position, and the initial position is 0 when t equals 0, so 1/2 0 squared plus c3, and it also turns out that in this case c3 is equal to 0. So using this information of the initial position, I find out that my position vector must be given where c1 was equal to 1. I'm just going to use technological magic and erase that. c2 was equal to 0, so I solve for that. And c3 is also equal to 0. And now I have my position function by taking the integral of my velocity function, making sure to keep the constants, and then solving for those constants. Thank you so much. That's it for today.